In this video, dear students, we are going to talk about the midpoint theorem and the median property. So let's start. What about the midpoint theorem? As you see, here is a triangle ABC, and D and E, as you see here, are given the midpoints of AB and BC respectively. So D is the midpoint of AB and E is the midpoint of EC. What does the midpoint theorem say? In any triangle ABC, as you see here, it's any triangle, not a special kind. If D and E are the midpoints of AB and BC respectively, as you see here, then DE is parallel to AC. So the segment joining the midpoints of two sides of a triangle is parallel to the third side and it's equal to its half. So DE is parallel to AC and DE is equal to AC over 2. This is the midpoint theorem in a triangle. Here is in a trapezoid. Here is a trapezoid. What's a trapezoid? It's a quadrilateral that has parallel bases. BC and AD are parallel bases. That's a trapezoid. P and N are respective midpoints of BA, BD, and CD. So we have that in triangle ABD. In that triangle ABD, applying the midpoint theorem in a triangle, we have that MP equals AD over 2, and it's parallel to it. Also, in triangle BCD, that one, so in triangle BCD, that one, PN, that segment, is parallel to BC and equals to half of it, applying midpoint theorem in a triangle. Then, what about MN from here to here? And this is called the median base. So MN is called the median base. Okay, because it's joining the midpoints and it's between the bases. So MN is equal to MP plus PN. That MN is equal to MP plus PN. Now evaluating and substituting, MP equals AD over 2 and PN equals BC over 2. Then MN is equal to AD plus BC over 2. And finally, this is the midpoint theorem in a trapezoid. So the midpoint theorem in a trapezoid says that the median base, which is the segment joining the midpoints of the non-parallel sides between the bases here, is parallel to both of the bases, BC and AD, and it's equal to their sum divided by 2. So MN is parallel to BC and AD, and MN equals BC plus AD over 2, and this is the proof here. That's the midpoint theorem in a triangle, and that's the midpoint theorem in a trapezoid. Let's continue what we have more. The converse of the midpoint theorem. So the midpoint theorem has a converse, as Pythagoras has a converse. Let's continue. Here is a triangle ABC. The given is that D is midpoint of AB and that DE is parallel to AC. So the given is different here. We don't have two midpoints. We have just one midpoint, which is D, and we have that DE is parallel to AC. Then we can discover or deduce that E is the midpoint of BC, and that's called the converse of the midpoint theorem in a triangle, and still DE equals AC over 2. So the midpoint theorem in a triangle, we have two midpoints. We can discover that the segment joining them is parallel to the third side and equals to half of it. The converse of the midpoint theorem, we have that one midpoint, one of the points is a midpoint, and we have that the segment is parallel to the side facing it, and we discovered that the second point is the midpoint of the third side. So the converse of the midpoint theorem is used to prove midpoints. So here, as you see, D is midpoint. Since DE is parallel to AC, we say that E is thus midpoint of BC. And by this, we proved that E is midpoint of BC using the converse of the midpoint theorem in a triangle. Training exercises. Here is a triangle ABC. The given is that D and E are midpoints. So D and E are midpoints. Let's code the figure. Here is for D and here is for E. If AC equals 8, so suppose that this side AC equals 8, you'd better code the figure. Okay? It makes things easier. Calculate D. So we have to calculate DE. That's very easy. How much is DE? How long is DE? So if AC is 8, D and E are midpoints, then applying the midpoint theorem, DE is equal to 4. It's equal to half of 8, which is 4. And that's the midpoint theorem in a triangle. Let's continue. What we have more? The median property in a right triangle. So let's start with the right triangle. In a right triangle, as you see here, it's right at A. The median relative to the hypotenuse, it is here AM. So the median relative to the hypotenuse, here it is AM, then AM is midpoint of BC, and here is the hypotenuse, is equal to half of it. That's the property of the median relative to the hypotenuse in a right triangle. So AM is equal to half of the hypotenuse, and since AM is the midpoint, then BM and MC are halves of the hypotenuse, then AM is equal to BM is equal to MC. ABC is a right triangle, M is the midpoint as I mentioned here, then AM equals BC over 2 equals MB equals MC as I mentioned. Conversely, there is a converse. If in a triangle the median is equal to half of the longest side in it, then this triangle is right and that side is the hypotenuse. So if you have that form, for example, if you have here a median and it happens that this median is equal to these sides, so it's equal to half of the longest side, then we discovered that this triangle is a right triangle, and that's the converse of the property of that the median relative to the hypotenuse in a right triangle is equal to half of it. Training exercise. Here is a triangle ABC that's right at A, and M is the midpoint of BC. Thus, what do we call AM? Because it's joining the midpoint, it's called the median. Prove that AMC is an isosceles triangle. That's a very simple training exercise. Let's think a little bit. M is the midpoint of BC. AM is the median relative to the hypotenuse because this is a right triangle. So we can apply the rule of the median relative to the hypotenuse, that's equal to half of it. Then AM is equal to MB is equal to MC, and thus AMC is an isosceles triangle because it has two equal legs, as well as AMB is an isosceles triangle for the same reason. And here is the solution. As I mentioned, since AM is the median relative to the hypotenuse, then AM equals BC over 2, which is equal to MB and MC. Then AMC is an isosceles triangle of vertex M, and the reason is because it has two equal legs. And now we are going to make a little revision for the remarkable lines. What are the remarkable lines? Let's start. As you see in this triangle ABC, CM, BD, and AE are medians. They are joining the vertices by the midpoints. So, since they are medians, they are intersecting at or concurrent at the same point G. This G, which is the meeting point of the medians, is called the centroid or the center of gravity of the triangle ABC. So, we've recalled the medians. So, the medians, again, are the sides or the segments joining the vertex to the midpoint. They are concurrent at a point called the center of gravity or the centroid. Here are the heights. Notice the heights means the perpendiculars or the altitudes. So another word for the heights is the altitudes, if you see it somewhere. The altitudes are also concurrent at a point that we call it the orthocenter. So the meeting point of the medians is the centroid. You have to differentiate between them. The meeting point of the heights is the orthocenter. And let's make it easier. Orthocenter is from orthogonal, so you don't have to forget it. Orthocenter from orthogonal. It's the meeting point of the heights. Also, we have the intersection point of the bisectors of the angles. AE, CD, and BF are bisectors of the angles, okay, as you notice here. So they intersect at this point and we call it I. It's called the N center of, it is the meeting point of the bisectors of the angles. And finally, we have the meeting point of the perpendicular bisectors. Notice the perpendicular bisectors are not necessarily going to the vertices. Perpendicular bisectors are segments that divide the sides perpendicularly into equal parts. So they are perpendicular, as you see here, for example, that one, it's perpendicular and at the same time it's a median. So it divides the side into two equal parts. That's why they are not necessarily going through the vertices, except in the equilateral triangle, and that relative to the base of an isosceles triangle goes through the vertex. Okay, so the meeting point of the perpendicular bisectors is called the circumcenter. The circumcenter is the meeting point of the perpendicular bisectors. So the circumcenter is the meeting point of the perpendicular bisectors. The N center is the meeting point of the bisectors of the angles. The orthocenter is the meeting point of the heights. And the centroid or the center of gravity is the meeting point of the medians. There is a property that I should remind you of. It is concerning the isosceles triangle. In an isosceles triangle, the median, here is the vertex, the median relative to the base, here is the base. If we have a median, the median relative to the base from the vertex is also a bisector of the vertex and a perpendicular bisector to that base. So median relative to the base from the vertex is also a perpendicular bisector and a bisector of this vertex. Similarly, if we have that this is a bisector of the vertex, then we can discover that it is also a perpendicular bisector. That's a property of the isosceles triangle. Now let's talk about the median property in any triangle. We talked about the median property in the right triangle, and now we are going to talk about the median property in any triangle. In any triangle ABC, let CM be the median relative to AB. And G, this is the centroid. I marked it here. I know how to mark it. If you want to know how to mark it, you just draw a second median and you will be sure that they are going to intersect here. And now we are going to understand the rules by what I know how to mark G. CG is equal to 2/3 of CM. That's a rule. And GM is equal to 1/3 of CM. That's all related to vectors, and you are going to know about vectors in the next year, inshallah. So let's now just focus on the rules and how to use them. Okay? So you are not responsible where the rules come from. Just focus on them and on how to use them. So again, if G is the centroid, which is the meeting point of the medians, and CM is a median, then from C to G is equal to 2/3 of that median. Notice that I divided that median into 3 equal parts. 1, 2, 3. 1/3, 2/3, 3/3. So from C to G we have 2 pieces. Then CG equals 2/3 CM. And GM equals 1/3 of CM. So as a result, I can notice that CG is double of GM. Training exercise, how to apply this rule. So this rule is to be memorized. From the vertex to the centroid is 2/3 of the median, and from the centroid to the base or to the side is 1/3 of the median. Using the above figure and the above results, suppose that CM, that median, equals 9. Calculate CG and GM. So using the rule, CG is 2/3 of 9. Then by dividing 9 and 3, we will get 2 times 3, which is 6. So by simplifying here, we get 3 here, and here will be cancelled, then we get 3. Again, applying the rule, GM is 1/3 of the median, which is given 9. So simplifying again, we get 3 times 1, which is 3. Notice this is equal to 6 and this is equal to 3, which is double as we said here. Here is another training exercise. In the given figure, look at this nice figure. In the given figure, M is midpoint of AB. So given that M is midpoint of AB, and G, that G is the centroid of triangle ABC that's colored in green. E is the symmetric of G with respect to M. That's the idea of symmetry. That means if E is symmetric of G with respect to M, that means that M, the point after with respect, is the midpoint of GE. Prove that AGBE is a parallelogram. Part B, prove that G is the midpoint of CE. How to prove a parallelogram? We can use sides or we can use diagonals. Here, it seems that we are going to use diagonals because, let's look at the figure. We have that M is midpoint of GE by symmetry, and we have that M is midpoint of AB by given. Thus, the diagonals GE and AB bisect each other at the same midpoint M. So to prove the parallelogram here, we are going to use the diagonals. Let's see the answer. M is the midpoint of the diagonals AB and GE. Then AGBE is a parallelogram. So again, M is midpoint of GE due to symmetry, and M is midpoint of AB, that's given. Thus, AGBE is a parallelogram because diagonals bisect each other at the same midpoint M. Now, how to prove that G is midpoint of CE? Let's start. CG, that CG equals double GM using the property of the median. So CG equals double GM. GM equals ME. So GM equals ME. So GE equals to double GM. Again, CG equals double GM. GM equals ME. Then GE is double GM. So by comparison, we have that CG equals double GM and GE equals double GM. So by comparison, we have that CG and GE are equal because both of them are equal to double GM. But since C, G, and E are collinear, then we say that G is the midpoint of C.